So on this page, you can see the different kinds of fiber interface connections available with SEL 411 relay. So for this example, I'm going to be using an SEL 411 relay. So we have two different kinds of fiber ports on this relay. One is IEEE C37.94 standard based, and the other one is a direct fiber link between the two terminals of the line. So the peculiar thing about the IEEE C37.94 is we can use that fiber port connection with any multiplexer. So we can have a relay and a multiplexer. Both of them can be of any vendor, different vendors. And if we use this standard fiber, then we can connect any, or we can connect different vendors relay with a different vendor multiplexer. There are also some technical specifications about those two fibers. The one common thing about about this fiber connection, or both of the fiber connection, is the data rate. Both of them transfer data at 64 kbs per second. So that acts as a common ground or a uniformity if you were to use them interchangeably. So there is an interchangeability option. So on this screen, you have the spectrum of all wavelengths laid out. So on your left, you have really small wavelength and high frequency gamma rays. And on your left or on your right, you have really large waves, but low frequency radio waves, which are really low energy as well. And in the center, you have the visible light spectrum. If your wavelength, if you increase your wavelength even far beyond the visible light, then you enter the infrared region. And just a fun fact, the infrared which we use in our CCVT camera applications generally use 850 nanometers to 1000 nanometers of wavelength for illumination, which is similar to one which we use in signal transmission between two terminals of a transmission line for implementing any protection scheme. So there are a few considerations which we should be taking into account while using fiber optics. Is the first one is there a data, is the data, if the data is synchronized or not, or in other words, is the channel symmetrical. The other one is channel redundancy. We can have two different channels or two different paths of fiber between our local relay and a remote relay. No coordination is required. By no coordination, I mean time coordination. And we could have, and while using a fiber, we should keep in mind that we might need a multiplexer. So what are the different kinds of protection schemes which we can use? So the first one we'll be discussing is the overcurrent protection. So, or the instantaneous overcurrent element, which is the 50 element as per the NSI standards. So for this element to work, we need a single current output, or if you're using a ring bus system, then you need the current contributions from both the breakers. into this transmission line. So we'll need a summation of two current analog inputs from the ring bus. All we need to do is set up a pickup value for the 50p element. So the relay compares the magnitude of um, each phase of the analog current with the pickup, and if this condition is satisfied, or if the relay sees the analog current magnitude higher than the pickup value, then it picks up, and you can assign that 50 element to the trip equation. So the next one for overcurrent protection is going to be a definite time directional overcurrent element. So this is quite similar to the instantaneous line overcurrent element which we just saw, but the one or the two different things or the two differences between these two is there's a time delay. We could add a time delay to this relay element, and this relay element is supervised. So for supervising this relay element, we use a torque control equation. So this torque control um, verbatim is derived or taken from the mechanical relays. So the torque control equation generally uses current polarization or voltage polarization elements. And the last one for the overcurrent protection is the inverse time overcurrent element, which is the 51 element. So this is a more secure kind of overcurrent element. So the operate time is inversely proportional to the fault current value, and as the fault current increases, the relay operation time also um, the relay operation time decreases. So it's inversely proportional. And on your right side, you can see how um, the relay operation time changes with the multiples of pickup. So as the multiples, so if you start off at the multiples of pickup value of 2, the relay operation time is the largest or the highest. And if you see at the very end, at the multiples or the 40th multiple of pickup, the operate time for the relay is the least. So that's where the name inverse time proportional or inverse time overcurrent element is derived from. And I've also shown an equation which gives you the operate time and reset time. One thing to note here is there is no electromechanical reset in this relay, but we can simulate um, that electromechanical reset time by using this equation. So now we'll be talking about step distance protection scheme. So for implementing a step distance protection scheme, you require both voltages and current inputs to a relay. As this is the impedance based scheme, the relay will calculate the um, impedance of the fault to see if the fault lies on the line or not. So primarily there are three zones of protection. So the zone one, if the if the fault lies in zone one, then The relay issues an instantaneous trip. There's no delay if the fault lies in its zone 1. Zone 1 usually covers about 80% of the line. The next comes zone 2. Zone 2 is um, covers a longer distance. It's about 120% of the line, but it's delayed. It's usually delayed about a couple cycles. 20 cycles is a typical value which I've seen. So zone 1 doesn't operate as soon as it sees a fault, but it waits for its zone 1 to operate so that it doesn't um, operate the remote end breaker if we can clear or the local relay can clear that fault. So it avoids nuisance stripping. Zone 3 is we can use zone 3 in multiple ways actually. Zone 3 can be um, looking in the forward direction or in the direction of the transmission line, or it can be looking in the reverse direction away from the transmission line. So it depends in which way you want to use this zone 3 element. But if this zone 3 element is looking forward, um, the usual delay on this element is about 60 cycles. And similar to zone 2, this zone 3 elements now waits for zone 2 to operate to avoid any nuisance tripping. And it covers about 200% of the transmission line which it is protecting. Zone 3 element is usually used um, in pilot schemes to notify the remote terminal relay about the direction of the fault, if it's on the line or it's not on the line. So here we take an example to explain how exactly the impedance is calculated. So on your screen you have breaker A, which is our local breaker, and you have a transmission line connecting our breaker A to the remote terminal. So in case of a fault, the the local PT will read a voltage reading, which is VF. So VF is the potential drop from the fault, or VF is the potential drop from the PT to the fault. And if we consider the transmission line current or the fault current as IF, then by applying simple Ohm's law, we can find the impedance to fault, which is nothing but the transmission line impedance. And this relay compares this calculated ZF value or the calculated um, impedance to fault value with our zone element pickups. And if the the impedance falls within zone 1, an instantaneous trip is issued. If the impedance value falls in zone 2, a delayed trip is issued. Um, just a few things to note. Angle of transmission line is the natural impedance, which is about 70 to 80 degrees. And the X-bar ratio of the transmission line is really important while doing fault studies and coming up with the breaker capacity. So this gives us the maximum available fault current at that local breaker. In this case, it is breaker A. So the X-bar ratio of the transmission line and the source impedance will give you the maximum available fault current, and the breaker capacity should be always greater than the available fault current. And when a fault occurs, there is a DC component in the fault current also, and this DC current is a DC component of the fault current is dependent on the X by R ratio. If you have a really long transmission line, the X by R ratio is very high. So this higher X by R ratio correlates to a lower rate of decay of DC component on the fault current waveform. And if you have a higher DC component, then you need a higher capacity breaker, because it's going to take a longer time for the arc to completely um, quench. So this slide illustrates the three zones of protection. Zone 1, which is protecting, so Z1 mag is the impedance, or the natural impedance, or the positive sequence line impedance magnitude of the transmission line. Z1 ang is the positive sequence line impedance angle. And as discussed before, the Z1P is the zone 1 element, which protects about the 80% of the line. Z2P is the zone 2 protective element, which protects about 120% of the line. And zone 3 in this case is a reverse looking element, which covers about 150% of the transmission line in the reverse direction. So on this slide, I have mentioned the three tests which we need to do to test out the distance element. So this is part of the commissioning process. The first test you do is the reach test. So how do you do a reach test? Keep the voltage constant, inject current just above and below the expected reach. So to calculate the current, you must be injecting into your relay. You use the same equation which we use to calculate the ZF, or the impedance to fault. The second testing procedure you should follow is the maximum torque angle test. So in this, start off with an impedance just inside your Mohs circle, and change the current angle in both directions until the element drops out. The last one we should consider is the Mohs circle plot. So in this, basically you're just plotting out the Mohs circle which we just saw in the previous slide. To do that, it's a very similar setup to the reach test, but you have to do that reach test for several points on the Mohs circle. So now we are going to be discussing about the directional comparison blocking scheme, which is a communication channel based protection scheme of the transmission line. So when you compare this scheme with the standard step distance, this has this has faster fault clearing times. So as this is a communication channel based scheme, you need a communication channel to send and receive signal. As this is a block based scheme, you will be sending blocks instead of trips. This scheme needs time synchronization, which is done by a local clock, a local GPS based clock. So again, this protection philosophy is based on sending and receiving clocks and not trips. Um, so this scheme is set up in such a way that um, if any of the relay doesn't receive a block signal from its remote relay, that relay is going to trip its local circuit breaker instantaneously. And it blocks the fast trip of the remote relay if the fault is not on the transmission line. So this scheme basically makes use of the zone 3, which is looking in the reverse direction to detect if the fault is not on the transmission line. So in this slide, I have 5 different fault locations, and we can go over each of those faults one by one. So the first fault is near. So let us consider the breaker A is a local breaker, and the breaker R is a remote breaker of the transmission line. So the fault at position 1 lies in the zone 1 of our local breaker A, and it lies in zone 2 of a remote breaker R. So in step distance elements based scheme, the breaker A is gonna trip instantaneously, but the breaker R is not going to trip instantaneously as it sees the fault in zone 2, and the operation for that remote breaker is going to be delayed by about 20 cycles. But in case of a DCB scheme, the operation with respect to our local breaker A is going to be the same. It's going to trip instantaneously. Now, if we move on to fault 2, it lies at the 50% of the line, and both the relays sees a forward fault, and both the relays trip their local breakers instantaneously, and no blocks are issued. But if you consider the fault 3, so that fault 3 lies within zone 2 reach of relay A, or our local relay A, and zone 1 of the remote relay R. So both relay A and relay R sees the fault in forward direction. They trip instantaneously as no blocks are issued. And if you compare the fault number 3 operation in step distance and in DCB, it's much faster from the perspective of our relay A. So in fault 3, a relay A sees the fault in its zone 2. So there is a delay associated with zone 2, which is about 25 cycles in this example. So relay A is going to take 25 cycles to operate. But whereas if you're using a DCB scheme on the same setup, relay A operates in 2 cycles as there is no block received from the remote terminal, telling the relay A that um, the fault is not on the transmission line. Now moving on to the fault 4, which is beyond the remote terminal breaker R. the fault uh, 4 lies within zone 2 reach of relay A, while relay B detects a zone 3 fault for fault number 4. So as the remote relay R detects a zone 3 fault, it sends a block signal to relay A saying that um, the fault is not on our transmission line, it's beyond our transmission line, and you're not supposed to operate. So it sends a block to a remote or local terminal relay A. In case of fault number 5, for our relay A, the fault lies in its zone 3, while the fault is in zone 2 of the remote relay R. So in this case, relay A issues a block to the remote terminal and stops the relay uh, at the remote terminal R from operating.